Hi everyone, my name is Jianting Ning. This is a joint work with my collaborators, Xinyi, Jianting, Shengmin, Jian, and Robert. This topic is on how to enable privacy preserving detection inspection on TLS with low hiding and faster connection establishment. Throughout the internet nowadays, we see the popularity of TLS is increasing day by day. According to the recent Internet Trends report, about 87% of today's web traffic was encrypted, compared to 53% in 2016. Similarly, over about 94% of web traffic across Google uses HTTPS encryption. However, since TLS ensures end-to-end secure communication, the increasing use of such end-to-end encryption to secure web traffic has hampered the ability of existing Middleboxes to detect malicious packets via deeper packet inspection on the traffic. Cyber attacks like malware and virus can be hidden and bypassed by the firewall into an organization's network. To overcome this problem, a practical solution named Transport Layer Security Inspection has been proposed. It is a secure process that allows Middlebox to detect the traffic, inspection the decrypted contact for threats, and then re-encrypt the traffic. It enables the Middlebox to have the ability to detect and re-encrypt every traffic that passing through an organization's network. By doing so, the Middlebox is now able to perform inspection. Note that to do this, either the client or the server is aware to be inspected. However, there are several issues about this approach. First, we must fully trust the Middlebox. Second, it violates the end-to-end security of TLS. Finally, the security of TLS may be weakened, for example, misuse or lack of experience while implementing such a system, which are the security issues highlighted by the US CERT. To address this problem, BlindBox was first introduced in SIGCOMM 2015, which allows the Middlebox to perform inspection over encrypted traffic directly. The general idea is to perform encrypted token match with the encrypted rules. It provides the property of privacy preserving in the sense that the Middlebox inspects the encrypted traffic without decryption. However, BlindBox comes with some issues. In order to perform inspection of encrypted traffic, first, setup phrase is required over every session. The double circuit approach of their setup incurs significant communication and computation overhead. The detailed communication overhead is about 97 seconds and about 50 gigabytes bandwidth for a 3000 rules setup. In more detail, there are 4 entities in BlindBox, namely the rule generator, the Middlebox, a client, and the server. A rule generator is assumed to be fully trusted, and the Middlebox is assumed to be semi-honest, which follows the protocol but may attempt to learn more than allowed from the messages it received. For the client and the server, we assume that at most one of the 2 endpoints is assumed to be malicious, but not both. Such an attack is the same as the attack in the traditional IDS or IPS, whose main goal is to invade detection. Note that here it is a fundamental requirement that at least one of the two endpoints is honest. This is because if the two malicious endpoints agreed on a private key and send the traffic encrypted by this particular key, detection of malicious traffic would be infeasible. BlindBox requires two phrases to perform inspection of encrypted traffic. The first phrase is called setup. The purpose of this phrase is to generate the encrypted rules for every session, such that the Middlebox can use these encrypted rules for inspection. And because of using double circuit in this phrase, it incurs significant computation and communication overheads. The security requirement here is that the Middlebox should not learn the session key, and the client or the server should not learn the rules. In more detail, as the BlindBox system architecture shows in this slide, as initialization, the rule generator will send tuples of rules and the corresponding signatures to the Middlebox. For every new connection, the client and the server establish a session key by passing through the Middlebox with a normal TLS protocol. It then performs the setup phrase with the Middlebox by running a secure multi-party computation protocol to establish encrypted rules. Later, the client sends two traffickers to the Middlebox. One is the encrypted traffic over TLS, which the Middlebox holds it for later decision. The other is the encrypted tokens. The Middlebox will detect there is a match on it. If the match is no, the Middlebox will pass both the traffic to the server, and the server just validates the traffic to prevent the client to attempt to invade the detection. A brief explanation on how the traffic is tokenization shows here. First, suppose the original message attack is tokenized into 6 bytes. So in this case, 3 tokens are generated by using a Windows-based tokenization. It then encrypts these tokens with the proposed encryption scheme so that the Middlebox could perform matching of them. Recently, a new protocol called PrivDPI was proposed. PrivDPI follows a similar architecture as in BlindBox and provides a similar privacy guarantee, but with improved performance. It employs different approaches on encrypted rules and tokens. In addition, it enables the property of session reuse. In more detail, PrivDPI follows a similar architecture as in BlindBox, but did some improvement over the highlight parts. A different rule preparation protocol is proposed, which allows a session reusable property so that the setup phrase is done for only the first session with the particular server. It also introduces a new reusable token encryption, which allows the client to reuse the encrypted tokens in previous session. The computation is more efficient and the bandwidth required is lower as compared to BlindBox. However, for BlindBox and PrivDPI, there still exists a considerable delay during the establishment of a TLS connection, since each client is required to run a pre-processing protocol for each new connection. Both the BlindBox and the PrivDPI do not provide the privacy of rules against the Middlebox. Most solution providers relies on the privacy of their rules in their business model. Given the increasingly popular based black box service, the privacy of rules should be preserved against those black boxes. In addition, black box and PrivDPI needed to perform the pre-processing for each new rules. Given the above security and privacy concerns, we propose PI, a new protocol for privacy preserving deep packet inspection on encrypted traffic for a practical enterprise network setting where the clients connect to the internet through an enterprise gateway. We first revisit PrivDPI and demonstrate that when the root domain is small, the Middlebox in PrivDPI could forge new encrypted rules that gives the Middlebox the ability to detect the encrypted traffic without any encrypted rules yet generate. More details could see our paper. In addition to provide the privacy of traffic, privacy of rules is assured against the Middlebox. PI also enables the establishment of a TLS connection with lower latency and without the need for interactive pre-processing protocol as in BlindBox and PrivDPI. In addition, PI is a dynamic protocol in the sense that it allows new rules being added on the fly without affecting the connection between a client and the server. The threat model is similar to the Middlebox and the PrivDPI, except for the new entity gateway. As in conventional network setting, the gateway is assumed to be semi-honest. That is, the gateway honestly follows the protocol specification, but may try to learn the plain texts of the traffic. The gateway may also try to infer rules from the messages it received. In our work PI, we follow similar architecture in BlindBox and PrivDPI, but we did some several improvements over the highlights part as shown in these slides. We start from a practical enterprise network setting where clients connect to the internet through enterprise gateway. The latest incurring pre-processing protocol is performed offline, so it is only executed once. Consequently, there's no per-use connection overhead. Any client can set up a secure TLS connection with a remote server without a pre-processing delay. A new pre-processing protocol is then introduced, and the privacy of the rules is assumed against the Middlebox. We call this property the rule hiding. In addition, the privacy of rules is assumed against the enterprise gateway and the endpoints. We term this property rule privacy. Now I proceed to explain how the pre-processing phrases works. Different from BlindBox and PrivDPI, this protocol is pre-executed between the gateway and the Middlebox. It is a three-round protocol. The gateway first chooses a random number and sends the GX to the Middlebox. The Middlebox then sends the root tuples to the gateway. Upon receiving the root tuples, the gateway calculates the XI for each root RI and sends the XI to the Middlebox. The Middlebox then computes the reusable randomness rules table, which is used to generate the session detection rule later. Finally, the gateway sends the initialization parameters to the clients within the domain of the gateway, which will be used during the token encryption phases. We next move to the session detection rule preparation phrase. A set of session detection rules will be generated in these phrases. These session detection rules are computed tailored for every session from the reusable randomness rules generated from the previous pre-processing protocols. The generated session rules are used as inputs to generate the corresponding encrypted rules during the traffic detection rules. During the token encryption phases, the original traffic is sent through the TLS. Similar to the BlindBox and the PrivDPI, we adopt a Windows slide-based tokenization approach as shown in previous slide. After the tokenization step, a client obtains a set of tokens corresponding to the payload. For each token T, a client runs the token encryption algorithm as shown in these slides. In particular, the token encryption algorithm takes a secret derived from the session key and the initialization parameters, the token and assault. The assault here is used to prevent the frequency attack on the payload. The Middlebox receives the encrypted tokens and perform matching over the encrypted rules table generated in previous phases. If any encrypted rules that matches, the Middlebox takes some action, for example, drop a message or alert the server. On the traffic, once the traffic arrives at the server side, the server will run token validation algorithm to track the traffic. In particular, the server will decrypt the message implied from the regular TLS connection and then tokenize it and compute the same as the token encryption used by the client to obtain ePRIT, and finally compare whether it equals to ET. If not, it will drop the connection. In practice, new rules may be required to be added into the system. As shown in these slides, the rule additional protocol is a simplified protocol of the preprocessing protocol. The Middlebox only needs to run a two-round protocol with the gateway, and this protocol is executed offline. The rule additional is seamless to the clients in the sense that the gateway can locally execute the rule addition phrase with the Middlebox without any client involvement. Our experiment run on the computer showed in these slides, and the CPU supports AES-N9 instruction, where the encryption of token and the encryption of rules reflect this hardware support. And for simplify the payload that we test do not contain repeated tokens, and we call a one-round connection be a connection from the client to the server. The left figures show the running time for a one-round connection with 5,000 tokens, and when the number of rules range from 600 to 6,000. It is demonstrated that Pi takes less time than PrivDPI for each cases, and the right figure shows the communication cost from one round connection and the same setting. The communication cost of PrivDPI grows linearly with the number of rules, while for Pi it is constant. And we then, the left figures shows the running time of Pi is linear with the number of tokens on the payload, the same as PrivDPI. However, for each cases, the time consumed of Pi is less than PrivDPI, and the right figure shows the communication cost and the same setting, similar to the running time. The communication cost of Pi and the PrivDPI are both linear with the number of tokens, but Pi incurs less communication than PrivDPI. We test the running time and the communication cost with 3,000 rules and 5,000 tokens when the number of newly added rules range from 300 to 3,000. As shown in this figure, Pi takes less time and bandwidth than PrivDPI. In particular, the communication cost of Pi is independent of the number of newly added rules, while PrivDPI is linear with the number of newly added rules. Finally, we have the following communication contributions in this work. First, we identify a limitation of a recent proposal PrivDPI, a new protocol is then proposed to provide a stronger privacy guarantee in the sense that the Middlebox cannot know the rules. Our new protocol also supports faster connection establishment and lightweight rule addition, which makes this work more practical than previous workers. Thank you very much.